Hi everyone, I'm Pragjyotish from University of Delhi, and I'm I'm a PhD scholar at University of Delhi, working under the supervision of Professor Abhidesh Prasad. So the title of my talk is Dynamical Systems with Similarity Dependent Coupling. So first, let me introduce what are coupled dynamical systems. So any dynamical system we describe with an independent flow, which is the term F here. And when we couple to such dynamical system, then we introduce another term which involves both the systems. So for example, in Stuart-Landau oscillators, we have the uncoupled version looks like this. And in coupled version, we have two Stuart-Landau oscillators where we couple both of them in one of the variables. In this case, this kind of coupling is termed as diffusive coupling. So let me say a few words about the independent dynamics of a Stuart-Landau oscillator. Here we have a limit cycle solution where in the XY space, wherever we start, we end up at a particular limit cycle whose radius is given by this parameter here, which I have chosen to be 1. So as you can see, with time, when I start from an X value closer to the origin than the radius, then it always ends up on the limit cycle, which has an amplitude of 1. So now when I introduce the coupling term, here x2 minus x1, and in this case, which is known as repulsive coupling, we have a term y1 plus y2. So when the coupling is diffusive, as you can see, x1 is equal to x2. Basically, both the limit cycles, both the systems settle on the same limit cycle, and their variables are identical, which is shown in this graph here. Similarly, when the coupling is diffusive, in this case also both the limit cycles end up on the same limit cycle, but they have anti-synchronization, or x1 equal to minus x2. So now we introduce both the kinds of coupling into the same coupling scheme. Then what we see is this structure, bifurcation structure. So before the parameter value, epsilon value of 2, we have two stable attractors. Then after, as we cross the value of 2, then we have what is known as amplitude depth, wherein both the oscillators settle at the same fixed point in this case, which happen to be the original fixed points of the uncoupled systems. Then as we move along and cross the threshold of 2.5, then we have what are known as oscillation depth. Here, both the systems settle at different fixed points, and they are created due to the coupling, these fixed points. So initial dynamics I'm showing here, when both the oscillators show periodic dynamics at epsilon equal to 1.5, we have two coexisting attractors, P1 and P2, which is shown in x1, y1 space. So for example, for the P2 attractor, we have two oscillators. We have the two oscillators settling at two different limit cycles in xy space. So these are what are known as inhomogeneous limit cycles. So I am showing the basins of the attractors here in x1 and x2, and I fixed y1 and y2 in this case. So I'm showing the three forms of dynamics which are apparent in this coupling scheme. So I'm focusing on the depth states here, sorry. So in amplitude depth, I'm showing how the two oscillators end up at the same fixed point. So this is the time series for the two oscillators. And for 3.5, as we can see, both the oscillators settle at two different fixed points in this, as shown here. And we have two fixed points which are shown in x1, y1 space. So for the fixed points, steady state FP2, we have two different fixed points at which the two oscillators settle, and which is shown in this time series for where t is plotted along the x-axis and x1, x2 along y-axis. So now we introduce a similarity dependent term into the coupling scheme, which is 1 by d. So D is something which grows smaller when the when the variables of the systems are similar. So this is very prevalent in physics. So we have in general, gravitational interaction, we have inverse square dependence, which is also a similarity dependent term. So in a similar way, we introduce a term 1 by D, which grows when the system's variables are similar. So firstly, I would like to show what happens when you introduce this similarity dependent term into the diffusive coupling scheme. As you can see, initially, when D was 1, both the oscillators settle at the same limit cycle. But in this case, the limit cycles are not the same. So basically, the introduction of the similarity dependent term has led to the formation of inhomogeneous limit cycles. So this kind of coupling is also used in mobile systems such as swarmalators. So now we come to the mixed coupling scheme and introduce the distance dependent coupling there. As you can see, now we have 4 attractors in total, and there is no eddy state. So the system jumps directly to OD state. These are unstable fixed points which are shown in blue. The attractors P1 and P2 initially oscillate around these 2 blue lines, then they settle at the fixed points Fp1 and Fp2. So this is a depiction of the process of inhomogeneous limit cycles to OD transition. As you can see, at epsilon equal to 1.0, the 2 oscillators are oscillating around 2 different fixed points. And when we increase the parameter value beyond a certain threshold value, then they settle into 2 fixed points. And this is shown through the eigenvalues also, using the very widely used stabilization technique. So here we can see after the threshold value, all the eigenvalues, real parts of the eigenvalues are negative. So similarly, the basins for these attractors and fixed points are shown in this figure, and they are marked accordingly. So we have also seen this transition in chaotic systems where we couple to ossler systems in the mixed coupling scheme, and then have introduced the distance dependent term, and we have seen similarly ISLC to OD transitions. So the main point of this study has been this finding out this transition from inhomogeneous limit cycle to oscillation state. And there are many aspects which we have not studied yet, like extending this work to networks of oscillators, and also studying swarmalators, systems such as swarmalators from that perspective. So these are the main 2 references from my talk today, and this is mainly based on this work in collaboration with Suresh, Abdesh sir, and Ram sir. Okay.
Hello, hope I'm audible.
Yes, I can.
So I wanted to ask you regarding whether such kind of mixed coupling is observed in any experimental systems or in any real life systems.
Okay, so we are actually working on that.
Okay.
And also this ISLC to OD transitions are observed in what are called as repressilators in genetic clocks in biology.
Okay, all right. And so this diffusive coupling that you initially showed,
yes.
Why did you choose to go with the symmetry breaking form and like only have the coupling in the real part and not the imaginary part?
You mean X and Y?
Yes.
Okay. Yes, because of the symmetry, because of the bifurcation structure we get. And this kind of transitions are not observed if you do all-to-all variable coupling, basically. So this is because we are coupling only in one variable, then we get suppose we are coupling in only y and introducing the repulsive coupling only in y and the diffusive coupling only in x, then we observe the AD states.
So have you tried all combinations of which variables to introduce?
Yes.
repulsive
After that
coupling
only,
and diffusive?
we have presented these results.
Okay, all right, thank you.
Any other questions? Yeah, if not, so I have a small question. Maybe you can take it as a suggestion. Have you studied the involved bifurcation in your second part of your work?
This one.
Yeah.
Yes. So your question was?
Have you studied the involved bifurcations?
Evolve bifurcation. No, sir.
What is the bifurcation mediating this transition?
Okay, so this is this point is basically this bifurcation is Hopf bifurcation.
No, basically, the transition is from inhomogeneous oscillation to OD state, right?
Yes,
so have you studied any bifurcations that mediating this transition? That's my question.
No, it is a direct transition. That was the result. Actually.
But still, whatever be the transition, there should be some bifurcation involved in it.
Okay, so we'll look into that.
Thanks. Thank you very much. Thank you.